Okay, we're gonna get started on homework for part A. Part 1 is explain the various ways you would estimate the diffusion coefficients in vapor and liquid binary mixtures, and how is the Vignes formula used in conjunction with the Stokes-Einstein equation, and why is it necessary? So, to start out here, I have our diffusion coefficients for liquid and vapor that are already known. And what we're going to do here is use our formulas that we've been working on and show how we can estimate these. So we're going to start first by just writing our, let's start with the Leonard-Jones. Yeah, I think it's spelled L-E-N Len-O-R. I might be spelling this wrong, but it's okay. And this is going to be equal to so our Leonard-Jones value is equal to a known experimental value, which is 0.00266. So that's already known. That's not like it's a constant. We don't need to necessarily know it. And then that's multiplied by temperature to the 3/2 power. And that's all of the numerator. And then in the denominator, we're going to have our PMAB to the 1/2. So P is just pressure. Our M is AB to the 1/2 is going to be our molecular weight to the 1/2, or it's going to be like the average of the molecular weights, I believe. And then it's going to be multiplied by our sigma AB, which is to the squared, which is our collision diameter. And then there's one more value, which is the omega, and that is the diffusion collision integral. I think so. Yes, so that's our Leonard-Jones equation, and this is used to find values for vapor when needed. So we can write over here vapor, and then liquid, we use Navier-Stokes, which we've used, or not Navier-Stokes, Stokes-Einstein. Sorry, I'm getting fluid mixed up. Up here, yeah, we have our Stokes-Einstein equation. That's used for liquids, so we can move on to that. And the Stokes-Einstein equation is a little bit more simpler. It's our DAB, same kind of thing. And then that's going to be multiplied by our Boltzmann constant times our temperature in the numerator, and then we're going to divide by 6 pi RA, and then our viscosity of B. Or sorry, yeah, our solvent viscosity. And then our RA is just the radius. Okay, cool. And then these two can kind of be worked together to just like worked in different ways to get our diffusion coefficients up here, or they can be used, let me write liquid over here. They can also be used in the, like up here it says in the Vignes formula, I think that's how you pronounce it. How do you spell it? F-I-V-I-G. And what this formula uses is it's going to use these same values that we just made. Oops, come on. Okay. This is going to use these same values that we already derived, but just used in different ways to relate and possibly solve for what's missing. and that will be multiplied by our other dBA, not XA. So that kind of explains a variety of ways that we could estimate diffusion coefficients. And this is only for binary mixtures, as it says up here in the problem statement, because it gets way more complex in other ways. So now we're going to move on to 2. Okay, I just drew our diagram down here to get started on 2. But the question here is derive the equation of continuity for component A diffusing in a unidirectional system with a rate of formation R sub A. So what I just wrote down here is just a kind of cube to show dimensions a little better. So we have our y dy, and then we have our dx, x, and z dz in our 3 directions. And then over on the left we have our naz, and on the right we have the same but in our dz. I also wrote down the known equation of continuity A, which is the gradient times our na plus d c base a over dt minus ra equals 0. And then I also wrote in minus out plus accumulation, and I should have like equals 0 here probably. Actually, let's not write that, because I don't know if that necessarily carries over. We're going to kind of be basing this integration on the idea of in minus out plus accumulation. So we're kind of just going to get started doing in minus out equals accumulation. So our n value is going to be NAZ, or NA2, I don't know why I keep saying Z, NA2, dx, dy, yeah, and then we're going to need a lot more space, or I need to start writing smaller. And then, so that's our n, so now we need our out, which is going to be n az dz, or sorry, dx, dy, same thing as before. And then we're going to add our accumulation constant, which up here is going to be ra, and then multiplied by, oh, we need dz in this context too. And then that is all going to be equal to delta CA multiplied all the way through, and then over delta T. Yeah. Okay, then we can kind of just simplify some things. We're going to get NA over DZ, DZ over DZ. Okay, and then we can simplify further. I'm just going to write simplify because I get lost sometimes. And then we're going to get our NAZ. I'm just kind of combining these fractions here. Sorry, I'm not very good at writing and talking at the same time. Still good. And then we just need our stuff on the right. Well, we need our RA. And then CA. And then it's going to be equal to change in CA, delta CA over delta T. Okay, looks good. What we kind of solved for here is our change in our molar flux rate. So we just need to do a couple more things to really demonstrate that how we're going to derive the equation of continuity up here. It's going to look a little different, but we'll get there eventually. So now what we need to do is Just simplify one more time. My gosh, I keep writing uppercase. And then over our delta t again. And then finally we can just set all of that equal to 0, I believe. And then we're going to want to get our everything on the same side. Yes, okay. It's starting to make sense. So we can just add over we can add this over and subtract by this. So we'll get delta CA over delta T plus dNAZ over dZ minus RA equals 0. Yeah. And then so that kind of is our known equation of continuity that we have up here. So we're gonna we have our negative RA, we have our dCA over dt here, dCA over dt, and then this extra term right here is just the gradient. So when we're seeing this here, this value is just equal to this value. So everything makes sense. It looks a little different, but it is the same. So now we're going to move on to part 3. Okay, now for part 3, we have explain how equimolar counterdiffusion arises at vapor-liquid interfaces when enthalpy of vaporization is independent of composition. So I haven't done a diagram yet, but I do have one that I have in mind. So we're going to start up here with our vapor condensing. So what this condense is, I guess, yeah. So what this question's kind of asking is how the energy change causes the kind of instability in our difference of vapors, so, or in our difference from vapor to liquid. So what I'm going to kind of show this is as vapor condenses, we know that it's going to make a very high energy liquid. And then what this kind of shows is enthalpy of vapor is released. A lot is released. So this area just shows as vapor condenses, we're going to get a really high energy liquid. And this very high energy liquid causes it to want to change its state again to be a vapor. So what this high energy liquid does is as more and more accumulates, it's going to want to vaporize. So we're going to have down here our liquid vaporizing. And then kind of the opposite happens up here. What we have next is going to be a low energy vapor. That's going to take away enthalpy. And then as more and more of this low energy vapor is being formed, we're going to make our final arrow here, which is going to make it want to condense. So that kind of so like the enthalpy will take the same amount of energy to vaporize to a liquid, or vaporize to a vapor, then it will take liquid to condense to water or a liquid. So that let me like causes here, because that kind of shows that the buildup of one thing causes the other, and it kind of just happens ratio that is similar. So yeah, that shows how our equimolar counterdiffusion arises at vapor-liquid interfaces. Now we're going to do part 4, which hopefully should only take a second. So let me write down a few things and then I will be back. Okay, I'm back. This last problem or last question is for reaction A in 2 to 2B on a catalyst surface. How is the total molar flux N related to Na? What's the relationship if it changes to 3A goes to B? So to start this, I'm just going to write, we know Na plus Mb equals N total. And how we're going to relate our Nt and Na, we kind of need to solve for Na. So we know 1A or A equals 2B. So that also means that negative 2A is going to be equal to B. Or 1B. I'll write 1B because it makes a little more sense. So now we can kind of add that back to our original formula. So we know 1Na plus what we have here is going to be 2Na is equal to N total. So we're going to have negative Na is equal to Nt. So what this just kind of shows is for the reaction A to 2B on the catalyst surface, the total molar flux is just going to be equal and opposite to our negative molar flux of A. So, okay, we're still good. So if the relationship changes from A to 2B to 3A to 1B, we need to do the inverse of that like we just did. So that would be negative 1/3 Na is equal to NB or NT, sorry. So then we'll add that back in like we did. So we'll have 1 Na plus negative 1/3 Na equals NT as we did above. And then when we add that, we'll have 2/3 Na is equal to, okay, 2/3 Na is equal to NT. So that just shows that the total molar flux is going to be equal to 2/3 the molar flux of Na. So yeah, that kind of wraps up homework for part A.